poor health, poor education, terrorism, and war. I personally am lucky to be involved in several different laboratories and institutes in various parts of the world. The University of Texas at Dallas, the Department of Chemistry at the University of Pennsylvania have laboratories in both places, separated by about 2,000 miles, and also a laboratory at Jilin University in Changchun in China, and institutes in my home country of New Zealand, and also in India, and also in Brazil. So for one reason or another, I have been fortunate enough in being involved, having been in the past and presently involved in quite a lot of collaborative research in various parts of the world. Now, the thing that I have found in the past, as I'm sure many of us here today, is that we'll have a very nice conference, and then we will go home to our respective laboratories next week, and next week we'll do exactly the same as we were doing last week. So the point is, how do we try to make sure that we do not do exactly the same next week as we did last week? And here, of course, we come to the real nitty-gritty of our conference. How does this stimulate collaborative research? Now, what we mean by collaborative research varies greatly, I think, from individual to another. At one extreme, it can mean, say, the synthetic person prepares a sample and then sends it off for some specific type of physical measurement to some other group, and results will come back good, bad, or indifferent, with very little interaction in between. The other way of doing collaborative research, which I myself have been very much more involved with, is a day-to-day interaction. Now, this can be done very inexpensively. The world is getting smaller. We have electronic communication. We have email. We have faxes. We have video conferencing, which is starting to become more common. But there's the good old-fashioned telephone, which I use enormously, using one form or another of the telephone cards. For example, I find that with the appropriate telephone card, I can keep in contact with my laboratory at Jilin University in China from Philadelphia at the cost of 1.9 US cents per minute. So it can be done very cheaply. And so I found, for example, that in keeping in contact with my research group in Texas from Philadelphia, about 2,000 miles apart, that I'm on the telephone at least once a day with my chief postdoc in Texas, and we will transmit backwards and forwards, say, copies of spectra by fax, and then we'll have this in front of us and we'll say, well, I don't understand why you get this absorption at 320 nanometers. We always find we get this at 302 nanometers. Now, is this the solvent you use? So we discuss things on an ongoing basis. And if one is considering, for example, the interaction, this, I think, is a very convenient way that we must remember that the means of communication available to us today are very, very different from what they were in the past, and I think we should use them. And that we can carry out real collaborative interaction. We all have our own ways of doing this, but I find myself that by using faxes, by using the telephone, by using email, and making sure that we are interacting at least, if not on every day, at least every 2 days, and saying, well, hi Joe, did you get my sample okay? And the person would say, no, it broke in the mail, and how many milligrams more do you need? So just to really have the personal interaction. I always like to say that science is people, that it comes down to personal contacts. You have to be able to get happy about things, the same things, you get sad about them, but I think I myself have found that keeping in contact with various parts of the world, which can be done relatively easily and very inexpensively today, but to keep in personal contact. And I think there are many avenues that we can well look into. That being a synthetic chemist myself, and particularly interested in electronic polymers, synthetic metals, I find that I myself, and I'm sure my colleagues, can learn so much from the first-class inorganic chemistry that has been done on various metal hydrides. But here I think we need to learn from each other. For example, our own field of specialization is electronic polymers or synthetic metals, conducting polymers. Now, as we well know from our inorganic colleagues, that many metals and alloys have great properties for the uptake, absorption, and desorption of hydrogen. What about synthetic metals? For example, we have synthetic metals which have free spins, they have poorly temperature-independent magnetic susceptibility, such a characteristic of metals. So how can we use these, considering them to be synthetic metals, but with an enormous variety of properties, where we can learn from each other? And the fact that the organic metals can be modified enormously in properties by adding various differing groups. I think the whole area of organic storage of hydrogen is now just opening up. We've just seen the tip of the iceberg. For example, Professor Wang from China, with his hydrogenation of aromatic species such as benzene as hydrogen storage media, and I believe we'll learn more tomorrow from work from Air Products. So I think that there's plenty of space for really good, viable communication. And I'm sure that now there are some comments that might be made, but how do we start? I think the first thing is to use email and the telephone, and whenever possible get together for a glass of beer or wine or the like. And as I always say, the most important work at a scientific meeting, the most important science, is written on paper table napkins. So I think we should make good use of the plenty of paper table napkins that are out here, when we have our morning and afternoon breaks and lunch, but particularly get to know the excitement and the worries and the fears and the disappointments of our colleagues in the various areas. So, are we going to do next week, when we get home, exactly the same as we were doing last week? And that depends on what we say to each other today, and particularly, I think, outside the formal part of the meeting. Mike, gentlemen, I don't know if you have other comments. I'm sure you do, which are very much more pertinent and germane.
I don't think that we could possibly have more comments that were more pertinent or germane, because I think you summed it up exactly right. And maybe we, in the panel that Richard will lead after lunch, well, first we'll have Laura Gagliardi's talk, and then we'll have the panel where we'll try to discuss exactly how we can make next week different from last week, with the goal of making the IPHE successful. So perhaps we should adjourn for lunch, or...
Mike, I do feel, speaking for myself, and I'm sure for many others, that we have the feeling, okay, we meet, we hear, work, okay, what do we do next? What is number 1, number 2, number 3, number 4? What are the specifics which would fit within the organizational structure that you have? Let's say that we've made our contacts. I know I have made a couple of very, very useful contacts myself. Okay, we can continue developing these, but if we want to develop them within the system, within the framework, I presume that you and your colleagues will be helpful in outlining to us, okay, what do we do 1 hour from now? What do we do? What is step 1, 2, 3, 4, 5, 6? I presume that this will be what paperwork, etc., is needed.
Well, I think perhaps Sunita might have a comment on that, the procedures of filling out, not procedures, but guidelines as to how to proceed with actually establishing a project.
Yeah, what we'll do on Wednesday during the wrap-up session is to really summarize where the IPHE is in terms of the proposal process. We'll say a little bit about the criteria, the evaluation team, and then specifically what the next steps are. So there's no very detailed process at this time. This is still in the works. So I think the main objective is for people to identify potential areas to collaborate. The real idea is really to leverage the work that's going on around the world. I mean, we heard so many excellent technical talks from around the world, and then start to develop ideas for projects. And then on Wednesday, we'll go through exactly what you need to do next to facilitate the whole process of submitting proposals and so forth.
That I think many of us would find extremely helpful, to get the specific mundane details. We can develop ideas. Okay, so what do we do on paper? No one likes paper, but it's sort of useful at times to have things written down, step 1, step 2, step 3, step 4.
Yeah, we'll cover that on Wednesday.
Great, thank you.
Right, I think we can take these things further forward in the afternoon session and also tomorrow. I've got one announcement to make, and it looks like Mike's got an announcement as well. It might be the same one, if you're lucky. Just a reminder for those that have got posters, if you could give an electronic version of the poster to the laptops that are just next to the stage there. So if you've got it on a memory key. Oh, right. So if you could deposit that on one of the computers that's in the internet room there. Mike?
That was one of my announcements. Thank you. I have a couple short ones to add. Once again, please check your contact information and make corrections at the registration desk. Fill out the survey about the meeting and also leave it at the registration desk. And if you check out tomorrow, bring your luggage on the bus. Apparently it can sit on the bus tomorrow during the day. So with that, I think should head to lunch, and we're going to be back on the original schedule for the second part of today. So we'll reconvene at 1:30 with a talk from Laura Gagliardi. Thank you very much.
After lunch, time's pressing on. It's a little bit after past now, so if you'll take your seats quickly. There were some announcements giving out this morning about the travel arrangements tomorrow. There have been a number of changes. An important one is that the baggage, if you're taking baggage out from your hotel, then don't leave it on the bus. You should take it to San Romano. Advice is that keep a check on the notices and things that are going up at reception for the latest information, as I suspect that this might change again. So I think there are some changes to the buses and timetable and stuff. So please do check regular intervals the information at reception regarding buses. Okay, back on with the technical session. I should have said this morning, just in case there was any confusion, you probably realised from the lack of good looks up here that I'm not Nydia. Unfortunately, Nydia couldn't be with us due to travel arrangements, and she sends her apologies. So you've got me in her place. And our next presenter is Laura Gagliardi from the University of Palermo. I knew I would get something wrong. Okay.
So, good afternoon, everybody. I hope after the excitement of the minister, you can now follow my talk. So, before starting, I would like to thank the organizers of this wonderful meeting for inviting me here and giving me the opportunity of presenting my work. So, I will talk about the prediction with quantum chemical methods of metal hydrides. And here the title is about MH12 and species also with larger numbers of hydrogen atoms. Okay, so the outline of my talk. I will spend the first 5 minutes in telling you a little bit about quantum chemistry. I hope you don't mind about it. Some of you know everything about quantum chemistry. Some of you maybe are less familiar, but the idea is to tell you what we can do nowadays with these computational techniques. And then we'll enter into the real topic, so metal hydride species. I will talk about this work that we have done recently on metal hydride clusters and how eventually we try to enlarge these clusters by putting them inside a Fullerene cage. So now a little bit about quantum chemistry, which is not directly related to hydrogen storage, but I hope you don't mind. So here I've tried to summarize some of key concepts that you have learned in chemistry textbook. So these concepts were developed in the 20s and 30s of the past century. So very briefly, the nature of the chemical bond, and then concepts like hybridization, delocalization, lone pairs, and various types of bonds that go back to people like Pauling, Mulliken, Huckel, and so on. Ligand field theory, Huckel theory for unsaturated hydrocarbons, and then the Hartree-Fock theory, which was a central field model developed first for atoms and then after that for molecules. And the Born-Oppenheimer approximation, which has already been mentioned this morning, which indicates basically the separation of the nuclear and electronic motion. So these ideas and basically all the equations of quantum chemistry were developed in the 20s and the 30s of the past century. But to cite Paul Dirac, these equations were just too complicated in those days to be of any use because they didn't really know what to do with them. The real breakthrough occurred in the 60s with the development of computers. So finally, it was possible to go back to the method which were developed in the beginning of the century and write computer codes to use those methods. So in the 60s and the 70s, the first methods were developed like closed shell Hartree-Fock for molecules and open shell for atoms. And then the first programs, like, for example, IBMOL, who was developed by Enrico Clementi. And, of course, I think many of you know about Gaussian. It has been mentioned in previous talks, who the first developer of Gaussian was John Popel. So now, back to the last 15 years. What has happened in the last 15 years? There has been a huge development of density functional theory, and all the ab initio results that have been presented in this audience, maybe most of them, have been obtained at DFT level. And it has been possible to study large molecules. Okay, here I cite biochemistry. This is not a biochemical audience, but large molecules are certainly important in biochemistry. And then there has been also some development in wave function-based method, like perturbation theory, and it has been possible to study electronic excited states for large molecules. Here I cite some of these methods. The idea is to go to methods which scale linearly with the dimension of the system, so one can really treat big molecules. And I would define these last 15 years like the Gaussian era, in the sense that if you now read chemistry papers, there is often a computational session, and most of the calculations are run with this commercial package Gaussian. And just to show you that this branch of chemistry had really an impact in recent times, I would like to remind you that in 1998, the Nobel Prize in Chemistry was awarded to John Popel and Walter Kohn, who were two pioneers of the area. So this is just to conclude what we can do nowadays with quantum chemistry. So basically we can study all sorts of bonds, and not only covalent or ionic bonds, but also, now the mouse, it doesn't work like a mouse. Okay, I don't have a mouse because I have, okay, maybe let's see if I can try like this. Okay, yes. So intermolecular forces, weak interaction. It's possible to study electronic spectroscopy. Here, for example, this upper thick line is an experimental electronic spectrum of trans-Steele-Bean. These lower spectra are calculated, and you see how good theory matches experiment. It's possible to study photochemical reactions, to determine molecular structure with an accuracy which sometimes is even better than what one can get from experiment. And here I gave an example of catalysis, enzymatic catalysis. And of course, it's possible to study also molecular spectroscopy, namely vibration of molecules. So I hope that you could stand these 5 minutes of general overview of quantum chemistry. Now let's see if it works. No. Okay, no. I thought I had understood how it worked, but now I'm stuck. Okay, sorry. Is it working? L'ho rimesso come prima, come me l'hai detto. Ok. E ora? Next. Okay, next. Okay. Oh, no. Okay. So now we enter into the topic of the talk of today. Metal hydrides. Of course, we have learned and heard many times at this conference that metal hydrides are interesting as potential hydrogen storage system, and the design target of about 7% hydrogen weight is considered adequate. So what we have been doing recently is to predict the existence with quantum chemical methods of some metal polyhydride clusters. I would like to tell you that, I tried to show you the powerful of quantum chemistry. One of the most fascinating applications of quantum chemistry, in my opinion, is to use it to invent new molecular species. Because it's, you need to have some imagination, but it's also less dangerous and more safe than to run an experiment. I mean, when I have an idea, I can just try it on my laptop. During conferences, I always run calculations. So it's really safe and it may be worth trying. So we have invented these new series of molecules with general formula MH12, where M is a group 6 metal, chromium, molybdenum, tungsten, and if you consider the ionic species, the idea works also with vanadium, titanium, manganese. And this represents a record for metal hydrides in the sense that in the literature there were known species with up to 9 hydrogen atoms, rhenium H9 2-. So having 12 hydrogen atoms is a record in this sense. Okay, here I reported some details of the calculations. I will not go through these overheads in details, but the idea is that we first try to use density functional theory, and this acronym B3LYP is just a functional, okay? And it's different or compared to some of the functionals that other people have talked about. And then when the system is not too big, we also compare our DFT results with the results obtained with wave function method. And this CAS-PT2 is a very accurate multi-configurational approach. And then we are chemists, so we like to describe our electrons moving in orbitals, and we like to use Gaussian functions to describe orbitals. Maybe other people, especially in the physics community, prefer to use plane waves, but we are chemists, we like Gaussian functions. And then, of course, we have to treat a metal. So metal has features like relativistic effects, which have to be taken into account. And in this case, we use some pseudopotential. And then what we do is to optimize the structure. So we let the molecule relax. And then we also compute harmonic vibrational frequencies, which is the fingerprint that we have a local minimum on our potential energy surface. And as I said, we confirmed the DFT results with some multi-configurational treatment in which we explicitly treated all the electrons and all the molecular orbitals intervening into the bonding. And what do we get? Here I reported the typical bond distances in the various species. So as you can see, we studied some neutral molecules and some anion and one cation. And you see we have typical metal hydrogen bonding of about 1.7 Armstrong, or 1.8 according to the species. And what is interesting is that we calculate a hydrogen-hydrogen bond distance of about 0.8284 Armstrong. And if you run a calculation at the same level of theory on an isolated H2 molecule, you get a bond distance of 0.74. So this long bond distance should be a fingerprint of the fact that you don't just have a hydrogen molecule which happens to be close to a metal, but you have some binding between the metal and the hydrogen bonding. And the ground state of this molecule is closed shell, a singlet. These accurate calculations told us that we don't have to worry about a close-lying electronic state. These are two of these molecules, how they look like. So chromium H12 has 6 H2 moieties, which are bound to chromium, while in tungsten H12 we have 4 H2 moieties and 4 single hydrogen atoms bounded to tungsten. We also try to understand a little bit about the energetics of these species. So what we usually do is look at simple formation reactions, like, for example, 6 hydrogen molecules plus a metal, which form this cluster. And it turns out that from very, very simple calculation, this reaction is endothermic when we use chromium, and it becomes exothermic when we use molybdenum and tungsten. So from a theoretical perspective, it would be easier to form the tungsten or molybdenum cluster than the chromium, but of course experimentally maybe it's easier to work with chromium than tungsten. And also these MH12 clusters are more stable than the smaller clusters like MH4 and MH6. And chromium H12 had been seen in the matrix by the group of Lester Andrews in Virginia. And actually, when we first published the paper, he said, we couldn't see your chromium H12, so how can it exist? But then he went back to his experiment on the basis of our calculations, and he could the frequencies of the larger clusters based on our predictions. So this is to show you how sometimes, theoretical work can also address experimentalists in their measurements. So now the idea is, can we make clusters with more than 12 hydrogen atoms? Of course, the more, the better. So we ask ourselves if species like titanium H14 or yttrium H15 are also stable. All these species that we have looked at fulfill the 18-electron rule. So in principle, also titanium H14 and yttrium H15 should be stable. So we just ran calculations on these isolated molecules. They turn out to be local minima from the mathematical point of view, but they have very long metal-hydrogen bonds. And if you look at these simple energy balances, they are not more stable than the smaller clusters. So titanium H14 prefers to go to titanium H4 plus 5 H2 molecules. So this is how they look. And you see here we have bond distance of 2.33 Armstrong, which indicates that there is not any real interaction between the hydrogen molecule and the metal. So the crazy idea that I'm working on and I try to look at is how can we eventually stabilize these species? And I said, why don't we put this metal hydride inside a Fullerene cage? And from calculations, it turned out that species like, for example, zirconium H4 or zirconium H14, scandium H15, and zirconium H16 are stable inside the Fullerene. And they have much shorter bond distances, metal-hydrogen bond distances, than when they are isolated molecules. They have all real vibrational frequencies, which mathematically means that they are local minima on the potential energy surface. And when I prepared my talk, I thought it would have been nice to mention the work of the chairman and also Dr. Zhao, but we heard a lot about this morning. So they have attached metal hydride outside the Fullerene cage, and this is beautiful work. What we have done instead is to put the metal polyhydride cluster inside the Fullerene cage. This is zirconium H14 at C60. Okay, the 0 is missed. And this is zirconium H16, so 16 hydrogen atoms bound to zirconium inside the Fullerene cage. And these are typical bond distances in these species. I reported the bond distances for the isolated molecule and for the molecule inside the Fullerene system. So, for example, you see zirconium H4, we calculate a zirconium hydrogen bond distance of 1.86 Armstrong, while inside the Fullerene cage, the zirconium hydrogen bond distance is 1.71 Armstrong. So it's about 0.15 Armstrong shorter. And then the same works for scandium H15, 1.87 versus 1.74. And also, for example, zirconium H16. You see, when we do the calculation on zirconium H16 as an isolated molecule, actually it's not stable as such. It prefers to go to zirconium H12 plus 2 H2. While if we run the calculation with the cluster inside the Fullerene, we have short zirconium H bonds, about 1.75. And as I said, the calculations give this structure with all real harmonic vibrational frequencies. So, of course, here I'm perhaps posing many questions, but there are many things that have to be understood, and in this I hope this audience may help me. So how can we make these species, if it's possible at all? And perhaps would it be easier to stick these metal hydride clusters inside a nanotube than inside Fullerene? And also, I ask myself if it's possible to have other species inside C60. I mean, in the literature, you read about metal ions or very small molecules. But for example, what I haven't found, and so I've run preliminary calculations, is, for example, methane inside C60. I think in the literature I tried methane attached outside to C60, but not inside. And calculations indicate that also the species C4 at C60 is stable. And while for the metal hydrides, the simple energetic balance indicate that the formation reaction are endothermic, for CH4 at C60, I mean, it seems this is at least isoenergetic to the separate items, C4 and C60. Okay, before concluding, I would like to thank the people I work with. So my group in Palermo, Francesco Ferrante and Remedios Cortese were two PhD students, and Cristina and Enza, who are master students. And then this work on metal hydride has been done partially in collaboration with Professor Pekka Pikko in Helsinki. And I use many quantum chemistry packages, and one of them is the MOLCAS package, which is very powerful, especially for wave function-based calculations, and this is developed in Lund in the group of Professor Roos. And my research is funded by the Ministry of the University and Education. And for future collaboration, well, I'm here to learn from all of you, and I hope to go home next week and be prepared to do new things. Thank you very much for your attention.
Thank you for that very interesting talk, and open for some questions.
To perform this kind of calculations, there is also another code available, the VIN2K code developed by Blacha and Schwarz. Have you tried to use it, or why you have preferred the Gaussian code? The second question is, what kind of computers or cluster of computers you have used for your calculations?
Okay, so the first question, I think that this program that you are mentioning is based on plane waves. I think it comes more from a physics community kind of approach, so perhaps the results are equivalent. I am a chemist, I'm trained to think in terms of basis functions like Gaussian basis functions. So this is a typical chemical approach, but I presume that in the end they should give the same result. And I mean, these calculations, at least those at the low level of theory, DFT, are not expensive at all. I can run them on my laptop, or eventually I just use PC clusters.
Yes, Keith?
In your calculations, do you calculate the wave functions of the protons and the zero-point energies associated with various proton motions? Because if you change the hydrogen-hydrogen distance, presumably a change in the proton frequency and therefore a change in its zero-point energy.
No, I can't calculate a proton because these are electronic structure calculations, so a proton has no electrons, so I can't run a calculation on a proton. Does it make sense?
Could you put the microphone on, Keith?
Sorry. You should have. You can simulate the molecule with the proton positions in the molecule, and then use the Born-Oppenheimer approximation to work out the energy levels seen by the protons and therefore what their wave functions are.
Yeah, I could. We haven't done it, but in principle this is possible. Yeah.
Yep, Max.
Yeah, the energy minimum that you calculated for the zirconium H16 and zirconium H12 and C60, is it an absolute minimum if you compare it to other possible hydride species in the C60?
No. I mean, the honest answer is no, because we don't know. I mean, we have a potential energy surface in many dimensions, and you are just like blind, you are moving. So you end up in a local minimum. So in principle, there could be lower minima somewhere else. I mean, this multiple minima is a problem that one should be aware of. The point is that we try to, I mean, what I try once I get a minimum, I try to dissociate the molecule, I mean, relax the molecule from this position and see whether it goes back or not. So these tests tell me that, I mean, I always go back to the lowest structure that I have obtained, but in principle there could be other minima because, yeah, I mean, it's a many-dimensional problem.
Okay, thank you.
We've got a question from the panel here.
Since you mentioned the word imagination, have you any theory about how this zirconium hydrogen 16 can enter a fullerene, or how you can get it out? Because in order to be useful, you have to find a way to get it out. And another more technical question, when you put all these things inside the fullerenes, have you seen any extension in the bonds of the fullerenes?
Yeah, I mean, first of all, the first question, not really. I mean, what I would think, but maybe it's just to open the cage and so open it on the top or on the side, but I don't know. I mean, here there are people who can say more about this. Of course, we allow the cage to relax, and it changes, it loses its symmetry, and the carbon-carbon distances increases. I think in the table that I showed there were a few numbers, but I can show them later on if you want.
Just a comment on this. I'm also a theoretician, but I have seen some very nice experimental papers doing some molecular surgery in fullerenes. So they open a small part. So a hydrogen molecule, for example, can penetrate, but not something like this, zirconium hydrogen 16. This you don't have to open it, you have to cut it in two parts.
Well, you could, no, because maybe they react inside. You don't have to put in the cluster, but the cluster could form inside. I don't know. This is just a thought.
I believe that people have put fairly large metals inside C60 and used them as kind of radionuclides, for the body, as an implant in the body. I believe that's been done. Anyway, I have a question, and that is that, Laura, you had some fairly favorable energies for the reaction of, say, heavy metals like tungsten with H2 to form the polydihydrogen species. Now, I don't remember the energies, but what do those energies look like if you now begin with tungsten metal?
You mean?
In other words, your thermochemistry is tungsten atom plus H2 to give the polyhydro species. What if instead, you instead of using the, atomization energy for tungsten, you use the experimental energy for tungsten metal?
I haven't tried it. I can.
Would it be favorable or not?
I mean, it would be, at least, I don't know about absolute values, it would be perhaps more favorable than chromium. So the trend that we get is that the lower we move in the group, the more favorable the reaction is. So I don't know about the...
But then again, the heat of vaporization of tungsten is going to be far larger than that of chromium.
Perhaps,
so
yeah.
Anyway, I think it would be useful to see that.
Yeah, thank you.
Right, just got time for one more question. Alberto?
First of all, I'm very impressed by the degree of sophistication of your calculation. Having been an experimentalist in the field, at this I'm structured with the neutrons and some calculation, with the Kubas compound on, I know how difficult it is to get even the right HH distance. So I have a couple of questions. In your manganese compound, the HH distance is terribly short. It's definitely shorter than anything that has been experimentally seen. The other thing is that you put a lot of H2 around the metal center. But then I had two problems. One question is, what's the dissociation energy of the HH? And the other thing is that I concentrate on tungsten. You have two classical hydride, and all the rest is H2. It's not that by chance a result of
I think I had
how you parameterize the core.
Four?
Yeah, because it's extremely difficult to get the difference between a classical and non-classical hydride being of the order of 2 to 3 kilo K. That was the first question. The second question is that I have a problem with the steric hindrance. Even if you put 2 H2 around the metal, like ruthenium, you start seeing the van der Waals interaction between the two H2 that they should be in plane and they're out of plane about 20 degrees. This is experimental result from Newton, just because of steric hindrance. Then if you put 12, what is the HH non-bonding distance in your compound? And I have the third thing. Then the problem is that
Can you please
want,
speed up?
if you are a practical chemist, you want to synthesize that. And we know that if you want to stabilize some H2, you need a phosphine, or in the worst case, you need a nitrogen-containing ligand. And that is going to occupy a coordination position. If it's an octahedral, it's very likely that out of 6, 3 will be the ligand to spread the electronic charge on the metal center. Now, in matrix
Alberto,
isolation technique, you see
your
H2.
question's going on a little
Yes,
bit long, and I
and
think
I would say I reversed the question. Do you have any idea how a pure synthetic chemist can proceed if he really wants a compound which is more stable, which is stable above, say, minus 50 centigrade? Thank you.
Okay, I think I will just answer to this last question because the others, maybe we can discuss them over coffee. Well, the honest answer is perhaps no, because, I think that from the collaboration of synthetic chemists who could tell us what it would be worth to them that we simulate, and our expertise in simulation, maybe something useful can come up. So I'm happy to have suggestions from you.
Thank you very much. And if we could end questions now, but if we could congratulate. Could we have all the speakers from this morning up here, as well as Alan? Yes, as well as Alan McDermott. Thank you.
No presentation. right. Okay, so I absolutely want to tell you that we have to finish at 3 o'clock. We don't want to run behind our schedule, so we're already about 15 minutes short for the panel discussion. Another reminder that is, I was reminded again before to start the panel, that the objectives of the panel are to initiate potential project collaboration, mainly to see what the barriers are in this field. For instance, what are the gaps, what should be done, and what we should focus on. I have some ideas that we just discussed before with some of the speakers that I would like just to throw to start the discussion. Plus, I have one written question from the audience. I will also submit it to the panel. In my view on this, as you have heard, I mean, we've heard all the metal hydride talks yesterday, and this morning all the carbon, and you see that the frontier between the two is getting some kind of mixed up. So carbon people are doing some metal hydride work, and not necessarily with the expertise or all the expertise of metal hydride people. So probably there is here a venue for collaboration, especially within the IPHE. Other venue for collaboration could be between theory and experiment for carbon storage, like why don't we design experiment for theorists instead of the other way around? And I would just like to start with this and see what feedback we can get from the audience.
So you're suggesting that experimentalists lead theoreticians more? I would say that the reverse is required, seeing as just in the area of hydrogen storage in general, not just in the area of carbon, but all of the bushes and trees have been shaken for all the ideas over many years, and I think it's clear we need some new creative approaches.
My idea was just to have some experiment designed to validate some of the theory, because theory is going on, and experiments are going on, and we don't seem to really be able to connect. I'm not saying to design the material. I'm not saying just to test some of the theory or do some tailored experiment to validate the theory in this sense.
Oh, I completely agree with that. Some well-designed experiments. I'm sure you have comments on this, Guido.
Okay, I think the first thing is to relate quantities, okay? You may or may not see it, but theoreticians nearly always speak of energies in terms of delta E's. It's usually in electron volts. The electron volts doesn't matter, it's easy to convert to anything you want, but it's delta E's. Delta E is the change in electronic energy, okay? Delta H is what people usually measure, the people that do thermodynamics, and that is the enthalpy, which is of course the energy at constant pressure. And that's a very different quantity, okay? And it's the quantity that's as close as possible to what is measured experimentally, which is the isosteric heat. That's the heat at constant coverage. You know, usually it's a function of coverage. So I think one of the that's one point. The other point was made by Shaheen this morning, and that is that when theoreticians speak of loading, they mean the system filled with hydrogen minus, the empty systems, and that is not true of the experimentalists. The experimentalists speak of people that do absorption measurements. I mean, the isotherms that I showed, the experimental isotherms, have on the y-axis the Gibbs excess, what's known as the Gibbs excess. That is the amount of hydrogen that's there in the system over and above the hydrogen that would be there anyway if the surface were not present. Okay, so right. Anyway, my first point is that we need to talk the same language when we speak quantitatively. Okay, and I think it's up to the theoreticians to sometimes also try to calculate delta H's as well as delta E's. Maybe a theoretician can comment on that and the difficulties of doing that and so on and so forth.
I mean, delta H's can be calculated in principle. It's just that you need more to determine more quantities than the simply electronic energy. So, but there is a computational thermochemistry. It's just an extra ingredient to add to your treatment, but it can be done.
But if it were done, I think we would be one link closer with the experimentalists. That's my point.
No, I fully agree with you. It's just that it's an extra treatment and you have to do it properly, because sometimes, I mean, especially in organic chemistry, they try to do thermochemistry, and if they don't do it properly, they get results which are totally meaningless. But it can be done, and I think it's a very important issue that should be addressed.
But it cannot always be done. That's another problem of theoreticians, and you know that very well.
Well, also experimentalists.
Can I comment on that? This is a very nice comment, and actually address a problem that looks, but is not very simple. And I'm speaking now as a quantum chemist. So, for example, energy calculation and a geometry optimization of a structure is one thing. Calculating the delta E is a different kind that, of course, can be done, but it needs another quite also hard calculation, at least if you try to do it in a quantum chemistry way. That means you have to calculate frequencies in order to have the zero-point energy, make the correction, and make... The thing is that normally, in many cases, delta epsilon, the energy, the difference, is similar and comparable to delta E. But when we're talking about weak interactions in systems like this, maybe it is different. And I think at least what we have to do is sometimes, occasionally, in some of the system, check if it is consistent, and make some corrections of it if we need it.
Yeah, it can be very different. For the hydrogenation of graphite that I had in my talk, it's as different as from 7 kilocalories to 4, and that makes all the difference as to whether you can hydrogenate graphite sheet or not, okay? In other words, between success and failure, so it's important for weak interactions.
Well, thank you. We'll go to another subject.
Yes.
Okay, the other subject has to do, as from this morning talk, I took a note saying the best probably material or carbon material is the one that can have 6 kilocalories, which translate about 20 kilojoules, or we prefer 25 kilojoules. And now we're talking about metal hydride systems about in the 30, 40 kilojoule would be a good metal hydride system. And we see that carbon alone, I mean pure carbon, is stuck around 1 kilocalorie or 4 kilojoules. So definitely we're talking about metal-assisted carbon. We're talking about putting metal on the carbon structure. But essentially we're putting metal, and we're using the metal to get more binding energy. We're getting to the metal hydride section. The other thing is, yesterday it was a question in the last panel about nano sizes that they might enhance absorption. The questions put to you is there a way to use carbon, okay, as a holder for nano-sized metal particle? It's a question. I wrote it probably this morning, and I had one question from the audience, Professor Suda, which is practically the same, and I would read it textually. Say, my basic question for carbon, are these carbon materials mainly a support for the metal species that bind the hydrogen? If so, does carbon have special property as a substrate over other mixed metal oxide as supports such as magnesium oxide, zeolite, etc., etc.? So this is probably a very good question for two things. Are we going to use carbon to make nano-sized metal hydride, finally? Or there's a synergy between the two? And probably more importantly, are there a way to open some collaborative project between the metal hydride community and the carbon people on this subject? I'm sure there'll be much interest from both sides. Anyone who would like to comment?
Maybe I should say something since I mainly talk about it. My feeling is that what we have done really bring the two seemingly separate field closer. Now I agree that, at least from our limited experience, I'm not sure that carbon is the only holder for these metal atoms. It could have other light element. But on the other hand, we do know that carbon has a rich chemistry. That rich chemistry may be very useful, and that is organometallic materials. You have thousands of them, and that give you this rich possibility to actually experiment some of these interactions. So I do think carbon is special, but there's no reason to believe other light materials is completely impossible. That I would say.
I would just like to comment and say, why limit ourselves to neutral carbon? Why not carbon with either a positive or negative charge on? Here I'm referring, for example, to field effect transistors, where in the gate you can change the properties of the gate very greatly by having the gate in a field effect transistor attached to either the anode or cathode. And this then moves into the whole effect of ChemFETs. That is where you have the gate of a transistor, which then reacts chemically in a sensing device as soon as one puts either a positive or negative charge on the carbon. And this, I think, raises a completely different concept, whereby if you use conducting polymers, electronic polymers, where you can either have a positive or negative delocalized charge on the backbone, depending on whether you have a p-doped semiconducting polymer or an n-doped semiconducting polymer. To what extent does the charge, which of course runs all the way through the body of the polymer, affect the interaction with hydrogen? We ourselves would be delighted, as I'm sure many other people throughout the world would be, if a theorist would do some calculations on the interaction of the dihydrogen molecule with the charged backbone, either positively charged or negatively charged, since they're both known experimentally, on the charged backbone of an organic electronic polymer. Bearing in mind, as I mentioned briefly this morning, that we know that metals and metal alloys have very interesting properties frequently for their adsorption and desorption of hydrogen. The whole field of synthetic metals lies wide open for study. We can, in the synthetic metal field, which has Pauli-type susceptibility, characteristic of the metallic state, that is temperature-independent susceptibility, it would seem that from the beautiful work that has been done to date on real metals and metal alloys and their absorption properties of H2, we have this enormous field worldwide of synthetic metals in which the properties can be tuned and have been tuned, as shown experimentally, by chemical modification of the backbone and pendant groups. So I think insofar as theoretical studies, if one could apply some of the delightful theoretical studies which have been applied to metals to synthetic metals, this would be a very great guidance to we poor, more simple-minded synthetic solid-state chemists. And I'm sure that many of us worldwide would welcome some calculations on such systems.
Yes, I think that's an excellent suggestion, and that do open opportunity for collaboration. And regarding the charge, that's your first comment. Our experience is kind of limited. We didn't look at the charge effect for the transition metal, but we did study the charge effect when we have this light metal doped fluorines.
Here I'm referring to some work which Ray Bachman at the University of Texas in Dallas he has talked about this at conferences but has not yet published it. And that is a fascinating effect when one takes carbon nanotubes as an electrode in a capacitor and removes electrons or added electrons to it according to whether you attach that to a DC anode or cathode. Then he can get some very remarkable phenomena here by activating single wall and multiple wall carbon nanotubes by having them serve as an electrode in a capacitor. So I think that it is perhaps desirable to think outside the box here. Whether it'll be successful or dismal failure, one does not know. But to at least consider in the calculations what would happen if you have carbon in which some of the electrons have been removed in the form of a capacitor or an FET, field effect type device, or in which electrons have been added, to see what effect that would have on the adsorption or absorption phenomena of H2 molecules on the material.
That's what I'm trying to say. We studied this, for example, boron-doped fluorines. In that case, we look at the charge effect. And there is an effect, of course, depending on the charge. In one case, the binding energy increase, and in the other case, binding energy decrease, as you can expect. But the effect amounts to like 10 to 20% of total binding. So it's a minor effect at this point. And the understanding is because when you charge it, you put a delocalized state. But really, the binding requires a localized state. So that's why the transition metal d orbital, which is highly localized, has that amazing effect. But of course, there are other effects that we haven't studied. Or we know, for example, when we have this titanium carbide, and we have this actually dissociation of H2, and in that case, the electric field may play a much important role. So indeed, it opens a lot of questions and area of research that we should look forward.
That's very interesting what you say. It would also possibly be of interest to extend such theoretical studies onto synthetic metals, electronic polymers, which of course are real metals insofar as Pauli susceptibility, the conductivity, temperature dependence, etc., as well as their magnetic properties. So one has a system of very, very well studied materials, both chemistry and physics, worldwide. And it would seem that this is actually an extraordinarily interesting area to investigate, to see to what extent the HH bond in dihydrogen would be weakened or activated. We mentioned this in the poster session, by the metallic properties of certain organic species. It may be a complete failure, probably would be, but it would be fun to know, and the results could possibly be of very great importance to the synthetic chemist and physicist to know how to modify the molecular weight, the chain, the polymer backbone conformation, the degree of crystallinity, etc., in order to move in a direction which may be beneficial to hydrogen activation. I think one other point that is of possible significance in the whole area of fuel cells, and that is the use of the elimination of high work function metals such as the platinum metals, and to use high work function synthetic metals to see if they could then act as cheap materials as a substitute for platinum metals as catalysts in various types of fuel cells. This, of course, I think being now particularly pertinent in view of the fact that the whole area of nanotubes, nanofibers of various types of synthetic metals has now been opened up and developed by various groups throughout the world.
Thank you. I probably should go to another subject, which is, as I said before, if we talk single wall nanotube and pure physisorption, it's clear that won't be used at least as room temperature storage media. So the avenues we're going on, you have the metal there, but also the idea was with the last presentation that to put a metal hydride in. The question is to the audience and to the panel is how we choose which metal hydride we should put in, because we should not probably, in my opinion, just we put a metal hydride. What family of metal hydride should we go after? Because after all, we're trying to enhance metal hydride's properties supposedly by getting the nanostructure. Any feedback from the panel or from the audience?
Well, okay. From our experience, the metal, the first thing is that if you want to utilize the d orbital, it has to be transition metal. And the second thing is that you want the element to be light enough. So that already defines what kind of metal you want to play with. And among the metal, of course, depends on what kind of interaction you are looking at. If you're looking at this molecular or dihydrogen absorption, I would think that something like titanium or vanadium, which is relatively easy to obtain, probably a good candidate. Even though the discussion that we put this morning is scandium, but I think some of the physical properties of the nearby metal are similar, at least to demonstrate the principles. That probably something to try.
Michael, any comment?
I agree with Shangbai, but to address another component of Suda-san's question, is in this case the carbon nanotube simply or the fullerene simply a support that's inert and doesn't really. I think the implication in your question is, could other supports be used, and is this just a way to keep small domains of nano-sized metals separated from one another. And I think that's not the case, really, in that at least the carbon lattices that we're imagining for holding these metal atoms now they're half of a complex, and so that the carbon framework in this case participates in binding and localizing those atoms, allowing the d orbitals to be presented then to the hydrogen environment. So maybe it's a question of degree, but I think there is a particularly specific function. And if you were to go to something like a zeolite surface or aluminosilicate, they'd be heavier frameworks, and they'd also be larger framework. You have this competition between the binding energy, designing the binding energy to be specifically where you want it to be for performance on board a vehicle, and determining how you can array these sites, a large number of them, in space in order to reach the volumetric requirement. And then the means by which you do this have to be with sufficiently light material so that you can meet the gravimetric performance. So I think in the case of the carbon lattices, there is a way to simultaneously meet all of those things. And I don't think that would be the case with aluminosilicates, for instance, or other types of zeolite structures.
It's more concerning your question about which metal. From a theoretical point of view, it would be very perhaps interesting to use also lanthanides or eventually actinides because of the F electrons, which are all at the same energy level. So in principle, there are these F orbitals which are there available for bonding. But I presume from an experimental point of view, working with lanthanides is even more tricky than transition metals.
Well, my question was, I was thinking system. Our purpose is not just to put any metal there. Our purpose is to enhance already a good metal hydride. In this sense, that's what was my question. If somebody's trying to model something, what kind of, don't forget we're doing that for hydrogen storage. So we should not start with a metal hydride with a poor storage quality. What we are trying to improve, and that was my question, if somebody's going to model, what would be the best, or what would be the metal hydride that we should try to improve, not just go at large. Second question, this time to Michael Hirscher. I just want to have his feedback on this. It seems that from my experience, we always relate when we talk of, we do this hydrogen adsorption as function or of surface area. It's a useful data, but it could be also misleading, especially for system design, because if you look some of the MAFs, for instance, you can get 5, 6, 7,000 square meter per gram surface area. But then what is the bulk density of the material? This is always the question, because we have two constraints on the system. We have the gravimetric, which is enhanced by the larger surface, but then we have the volumetric. And from our experience now, when we design physisorption materials, we always look at a compromise between surface area and bulk density. Okay? Do you agree with that, first of all? And second of all, there is a way that we should not probably, when we stress hydrogen storage, hydrogen physisorption, try to always to think of system-wise, not only, optimize capacity of one factor.
Okay. I agree with you, but as I told in my presentation, the limit is the density of liquid hydrogen. I think you cannot get it dense, although if you use physisorption, I think you cannot fulfill the DOE goal for 2010. So one has to keep this in mind, but there may be a lot of other advantages that you may not need huge heat management or something, because the heats involved are small, and so you have other advantages which may, if the constraints on the gasoline price or something change, then this may change.
Okay. I do have a comment on this, probably we can pursue with Michael. DOE is interested, it seems, in funding a study on, I'm not making a formal announcement, but what I understand is that looking for system design, because see what, for instance, what physics option could do or anything, there already some effort in, and that would be probably an area where people from other countries are interested in system design or modeling or anything, we can get together to see all the factors that could be important for such a technology. So if somebody is interested to cooperate on this subject, probably there is one of the subjects that could be, a project could be started within the framework of IPHE. Michael, please.
I'm hoping that maybe we could get the automobile the representatives from the automobile companies who are here to comment on the how much would we be willing to derate the volumetric requirement for a conformal system, like some of the possible advantages associated with a low temperature physisorption system that would operate at lower pressures would be that you could have the packaging engineered into the vehicle, perhaps. And from what Scott Jorgensen had mentioned to me, that there was some, I looked in the table to see what the derating on the volumetric goal would be if that storage system could be truly conformal, and I couldn't find it. So maybe you can help.
Yeah, I'm sorry you couldn't find it. For starters, we'll have to look into that. The number is 20%, so that if it's fully conformal, you can take 20% more space, or you can take 20% off the energy density number, whichever you prefer. And the reason for that is obvious, that in a cylindrical geometry, a lot of space goes to waste, basically. And so if you don't waste any space, you get more given to you. On sort of a parallel note, I'd like to endorse the idea that we're looking for ways for different branches of science to collaborate, but I think there's a lot of room for science and engineers to collaborate, or maybe get the metal scientists, the physisorption scientists, and the engineers all together. We've talked about the amount of energy that's necessary to move and how hard it is with the metal hydrides because it's a big number. But even with the physisorption systems, heat transfer is a real challenge. Even though you're only moving 6 kilojoules, you're moving it uphill. And any engineer will tell you it's a lot easier to move heat downhill from a hot place to a cold place than it is from a cold place to a hot place. So dealing with 6 kilojoules at liquid nitrogen temperatures is also a big challenge, and one that probably getting the engineers in early would be a good idea.
Sunita, I see you're holding the microphone. Do you want to comment?
Yeah, I just wanted to add, Michael, for people who look on the website for the explanation of the targets, there is a link that actually describes each target. There's a paragraph description on how they were set, and if you look at the paragraph describing the volumetric capacity, that's where it mentions the 20%.
Just to make a comment on the question about volumetric density with the MOFs, and I mean there is some work looking at trying to put extra ligands in there so it's not a structural ligand, and that would increase the surface area. You're creating surface area within the channels rather than making your structure larger. So that's a possible way in which you can counteract the problem of volumetric density. But also, I mean, something that I would have thought was most interesting in the MOFs is to try and change the chemistry of the walls themselves and these reticular MOF structures. And I would like to see more work going in that area. or maybe trying to combine the ideas from the nanotubes and looking at Kubus type complexes. Could we get that type of thing occurring in a MOF structure?
I think that is a great comment, and I think I view the MOF materials as another system where you can, in principle, maybe in the way off in the future, maybe never, but control the energy of the metal species at those vertices. Right now, I think Shangbai made the comment that if they're oxide tetrahedra, they're chemically inert, and I think the unique feature about the transition metals on a fullerene, as Shangbai said, they're active. If we could come up with new chemistries with kind of that same paradigm, something that might be easily highly easily manufacturable and form regular arrays, and still need to reduce the amount of unused volume, so they need to be. It's not. I agree that the comment that a material has a tremendous amount of surface area, therefore it's a good one. No, I should say void space. I think MOFs were quoted as having the highest proportion of void space of any material, and that works against you. So if you combine new chemistries with low amount of void space to get the right binding energy, I think the MOFs may provide another kind of playground, if you will, to investigate that idea.
In just listening to the conversation, it strikes me that we speak of physisorption and chemisorption, and maybe we are mentally hung up by these words. Perhaps what we should do is just dispose of any attempt to distinguish between physisorption and chemisorption, and just talk about the actual numbers, the actual interaction energy of H2 with the substrate, whatever it is. I'm just throwing this out. And if we do choose to use the words, there is at least one definition, and that is that chemisorption will be strictly limited to dissociative chemisorption, and physisorption could be limited to the HH bond being retained. But even then, it's very important to talk about things in energetic terms. We have to allow ourselves mentally be open to the situation that Mike Eben always talks about, a strong physisorption. In other words, what he's talked about, and he said first thing this morning, is something which is not 1 kilocalorie, but it's between perhaps 4, 5, 6, 7 kilocalories, or if you like, around about 25 kilojoules per mole. So anyway, perhaps we ought to not box ourselves in by such old terms of catalysis as physisorption and chemisorption, and think more of it in terms of actual numbers of energies. In that way, I think we may make more progress. Just a comment.
Well, I want to make comment on your comment. You see, when at least from what we are doing, we can certainly see qualitative difference between physisorption and chemisorption. In particular, the distance. The distance in this case, if you have a physisorption of H2 molecule, is typically more than 3 angstrom. But when you have what we call the Kubus interaction, it becomes only 2 angstrom. So it really has a jump in the distance. And in terms of interaction, they're different. Because here, if you notice some of my result, that you see a strong hybridization of electronic state when you have what we call chemisorption. But when you have physisorption, basically it's really difficult to find the trace in the electronic structure that is responsible for that kind of binding. Of course, I think energy is important, but that's probably why we still use the term, so to make this difference.
Okay. We still have about 13 minutes. I would like to engage the audience at this stage, so any intervention from the audience side, please. Yes?
Just going back to that last point, I mean, surely the difference in categories are between the situations where there is something like a molecule present and something where it's isolated protons. And this shows up immediately in the neutron scattering because you have the rotational level from the molecule, but what we're seeing is that energy shifting down as the hydrogen-hydrogen distance increases until such points as it disappears. But that's the division between the physisorption and the chemisorption, presumably.
So if I understand well, you have neutron scattering and you need some samples. So what kind of sample would you like to have people to prepare?
Big ones.
Okay, all right. Beside the big one story, what else? I mean, what kind? That's what we're trying to say. Is there is a way that we can design experiments? I mean, this is an experiment, but what shall people, let's say, try to prepare for those experiments?
We are very interested in samples which are showing, of course, greater heat of adsorption, because that's where we understand the mechanisms. At this stage, it doesn't terribly matter whether they have very large surface areas, because if you understand what you're doing, then you can begin to design something with a bigger surface area.
Okay, so you're looking for any sample, any interaction, anything. That's it?
Anything with a stronger interaction than the 3 kilograms.
Yes, please.
Excuse me if I make a step backwards concerning the clustering of hydrogen around a metal. If you have a metal in a lattice, for instance titanium, the metal must obey the lattice rule. So the metal goes to in substitutional position. The particle, the moving particle, excuse me if I speak from a physical point of view, the moving particle will find a periodic potential imposed by the lattice. Around the trapping center, the site energy is deepened by banding energy. You heat, so you have a trapping center, you heat the sample, and then you have hydrogen evolving. In the case of a chemical bond, it is a little, question is different because you have to take in consideration the enthalpy of extraction. For instance, you consider a void. The previous work was theoretical. I'll mention experimental data. You consider the organic calyx arene. Calyx for arene is an organic structure made of carbon and balls. Balls. They combine themselves and they form voids. So it has been found that these voids can store methane. But so hydrogen is bound to carbon. So if you then have to extract hydrogen, you have to burn methane. So there is no point to store methane. And then when you extract, what do you extract? Again, methane, and you must burn to get hydrogen, you get CO and so on. So this should be taken in consideration. The other thing is that I heard that only 2 possible states that have been considered now. So the physisorped hydrogen, chemisorped hydrogen. Physisorped is absorption on the surface, the molecule, and so on. The second way is a chemisorption of hydrogen, so in a bond. There is a third way, so the lattice is the 2-dimensional lattice in the carbon nanotube neutral, or the 2-dimensional lattice can trap, be the host of a substitutional atom and impose its rule, as I said before, that this is the third way that has not been taken into consideration. So we have low temperature experiments in carbon nanotubes indicating the presence of a process that cannot be, hardly can be due to the molecule in carbon nanotubes because it is at too low temperature. that obeys quantum mechanical rules, features typical of quantum behavior of atomic hydrogen in protonic hydrogen in metals. So this third way should not be further neglected.
Yes, please.
A point that has not been considered up to now is that our research is addressed to possible applications. So up to now, we are used to work with a very little quantity of material, a gram or less. But the question can be, there are already materials sufficiently studied to be good candidates for attempts of scaling up, because a kilogram of material may behaves in a very different way than 1 gram.
I completely agree with you. Actually, we're starting collaboration with Michael to have some this order of samples just to do some basic measurement and experiment with it. And this is a collaboration we also wanted to start within the IPHE. If you have other suggestions, it will be welcome to collaborate and see what we can.
We can meet separately.
All right. 5 minutes left. Any more questions from the audience or intervention or a collaboration avenue? So if I understand till now, I mean, I've tried to just make a kind of point summary of what we have said. I mean, first of all, probably there is a way to find, try to design some experiments, just at least to validate some of the theory. So we will have some validation at one step of the process. The second one, and to see how to initiate something between metal hydrides and carbon, it seems, because as I saw two presentations on carbon C60 today and graphites with single wall nanotube, there might be some enough synergy there to probably start something along that side. Scale up, of course, of the small graphite, and that I agree with you 100%. We need not only to scale up samples, we need to have some being more thorough in treating samples, because as you saw in one of the presentations this morning, with the same sample, they got 6 different results through the process going from unpurified to purified. So most of the paper we see, we don't know how it was purified, how it was treated, how it was processed. And plus, probably we have to have more effort to make more characterization of the same experiments, because people are good at measuring density, people are good at having electron microscopy and everything. Probably we should have a collaboration at this level too. Okay, now I'll thank all the speakers. Thank you for your contribution, and the panelists. And probably thanks again. And probably we'll have 3 minutes for the next, to leave the floor for the next session. Thank you very much.
Then it's time to start this session on off-board storage, stationary application, and hydrogen transport. So everyone can sit down, then we can start the first presentation. Okay. Yes, take that.
Okay, I will take it next to you. No, because I was waiting for everyone. I have just two announcements for people leaving tomorrow. There are only 2 buses leaving in the afternoon tomorrow. Only 2. It's not possible to change the time schedule for these buses. One is 2:45 p.m. and the other one is 4 o'clock. Both buses go to the Pisa airport. I remind you just to sign up the sheet in front of just in the entrance. In case that you don't have on time with your flight with these 2 buses, unfortunately you have to take the train. It's not far away, and the train schedule will be posted just at the main entrance, the registration area. The other communication is for people just presenting posters, as announced this morning. In the internet room, there is a computer with a label like this just below the display. We hope that everyone is willing to share the presentation also in electronic version to be downloaded to put on a website. You go there, and there is a directory on the desktop, and you upload your poster presentation in any form you have, a PDF or a PowerPoint or any, and you can put there. Will be very helpful to us just to have all the poster presentation there, and we can put on the website just shortly after the conference. Thank you.
Okay, then we start the scientific presentation. My name is Bjørn Haubach from IFE in Norway, so I'm going to very pleased to present the first speaker. It's Daniel Fouchard from CNRS in Grenoble in France, and he is going to speak about 3 classes of metal hydrides, the History EU Consortium. So please.
I'd like to thank the organizers that provide us the possibility to give a summary of present activity on the ongoing program History, developed under the scheme of European Communities. History is a consortium built in 2001 and start effectively end of 2001 and gather 4 partners from university and research centers and 5 industrial partners. And in this consortium, we aim to analyze the possibility to upscale what I would like to say, not exactly well-known, but well-established metal hydride in order to develop application and to process both in industrial scale and also to develop a pilot tank and also to develop a mass tank for application. How it works. Okay. So we decided to work on 3 types of metal hydride. The first one is a low temperature metal hydride type, BCC type of materials. And so we like to get materials for application up to 8% reversible hydrogen and working at rather low temperature. The second class of materials we have considered was magnesium activated hydride, and so it is a more performant metal hydride in terms of weight, reversible weight, and we aim to develop application for about 6% of reversibility. And a more prospective class of of materials was to consider the alanate, lithium, potassium, and sodium alanates. And so potentially it's expected to cover a range of 5 to 10% reversibility, weight reversibility. So the BCC type of metal hydride was designed for a static system, and so not mobile, but due to the limited range of reversibility. And so the first work we have to handle was to upscale pilot production of well-known BCC materials, but also to adapt the formula in terms of the type of upscaling available in the industry. Besides, we have developed numerical computation to develop effectively prototype tank, and it is a very complicated problem because we have to order and we have to consider many parameters, heat, pressure, and cold, and heat transfer, thermal gradient, time, and so on. And finally, a large-scale tank was constructed and charged with hydride, and now is going to be applied in a building in Stockholm. So I will describe step by step the different type of works, but you have to know that we have had a very nice concerted work in between the institutions and also industrial partners. So the first class of metal hydride we consider BCC type of alloy was based on the ternary system, titanium, chromium, vanadium only, and so you can see there the type of microstructure we developed. It's not a pure titanium, vanadium, chromium, but we have installed interstitial phase in order to make better the kinetics of hydrogen uptake. So we have studied by use of neutron diffraction and the alloy, and also systematically the alloy and systematically the hydride in order to verify the quality of the material and to see that, for example, this is a perfectly disordered alloy. So in order to turn to the application and to be able to deliver BCC metal hydride well applying in the range that was required for the use of fuel cell, you have to know that in this range of titanium, chromium, vanadium ternary system, we can obtain different type of plateau pressure and different extension of the plateau pressure. And typically, this type of BCC materials, when it is hydrided, transform from BCC type of hydride, and the mass hydrogen uptake consists to transform the BCC to FCC type of structure. So there is a martensitic phase transformation that should be accounted for. And it is interesting to know that the unstable part of the phase diagram, metal hydrogen diagram, concerns mainly the FCC type of material. So we have to try to develop the best formula to decrease as possible the stability of and to increase as possible the extension of the FCC hydride. So for this doing, we have also been interested to develop bond structure calculation, and for example, I don't describe in detail what we have performed there, but we have a poster in the poster session, and so it is helpful to consider this approach to determine the stability of the BCC and to the FCC metal hydride. So it's possible to define different class of stability, different range of stability, different range of thermal stability. And so we have worked on a certain number, maybe 10 to 15 formula effectively. And now we have been able to deliver BCC type of materials that can work at rather low temperature. For example, between 20 to 60 degrees, it should be able to absorb reversibly about 2.1, 2.2% maximum hydrogen. This is the best achievement we got, and so we have a look about the stability, because the BCC are known also to be, for certain case of formula, to be rather unstable. So we have a start to analyze the stability with the cycling of this type of metal hydride, and it appears particularly stable. So the second class of metal hydride we have considered, it is a high temperature magnesium activated metal hydride, and for that we have considered only the possibility to activate magnesium by using metal, for example titanium, vanadium, niobium, and other type of intermetallics. Because we know that this type of oxide, for example, can be used as well to activate as catalyst the magnesium powder, magnesium hydride, but they are known also very toxic, and so we prefer to work with this type of catalyst. So the work was performed by using definitively the classical ball milling technique, and so we aim also during this work to get a more fundamental insight about how works the interface between the catalyst, for example, niobium and vanadium, and the magnesium grain, for example. This interface is very, very sensitive and very important in terms of very high kinetics of charge and discharge. Also, we have evidence that when we ball mill for a certain time at a certain energy, metal magnesium hydride with a catalyst, after one cycle, which we got effectively very amorphous, many defects has been installed in the materials, but after one cycling, it is very interesting to know that the magnesium powder crystallize in very small, beautiful sized nanocrystalline of magnesium. And this is a very interesting point, because it is known that hydrogens can diffuse very actively in between the small size, maybe 20 nanometer single crystals. Also, we have considered that the catalyst act actively on the kinetics. For example, when we ball mill magnesium with titanium or with the niobium or with vanadium, we saw when we look about different time ball milling that first the catalyst is hydrogenated progressively, and so for all the material we use, and also when we have performed in situ neutron diffraction experiment, for example, starting for fully desorbed materials, we can evidence and we can confirm that has been shown first by Jacques Huot on magnesium, that first the catalyst uptake hydrogen, and after only magnesium is formed, magnesium hydride is formed. So the mechanism is effectively a door mechanism, not exactly a catalyst mechanism, but hydrogen penetrates in the grain of magnesium via the catalyst, so-called catalyst materials. So we have systematically analyzed the kinetics, and so we can get, for example, 80% of hydrogen uptake in the magnesium in about 2 minutes of when the ball milling has been properly achieved, and using properly the good catalyst and the size of the grains of a good catalyst. So many parameters are very important to consider in the reactivity of so-called catalyzed magnesium hydride. And so we got very nice reactivity as many groups in the world, but it was to achieve our best knowledge on this type of materials. Also, when we desorb materials, it is possible to desorb very effectively and rapidly magnesium. So we have verified, and so we have verified by a comparison of how material we prepare in lab and also material prepared in the company. For example, company working with us on the magnesium hydride, that the kinetics properties of both material we perform, we achieved in the lab and was also prepared in the company obey exactly to the same kinetics law. The third class of metal hydride we have considered is light metal hydride LANET, but before a lot of effort has been made also parallel, for example, at the University of Stockholm. And for that, you have also another poster that can describe you can show exactly in details what has been done in that way. So it has been possible to, the group of Stockholm can stabilize new materials with excellent hydrogen uptake, for example, magnesium niobium, magnesium vanadium, and magnesium titanium materials. And these materials exhibit very nice hydrogen uptake, but unfortunately these materials are not stable. If you completely desorb this type of alloy, this type of ternary hydride, so the alloy is not stable. But it should be interesting now to consider that this type of materials that is very metastable should be one of the active part of the interface between niobium, titanium, and vanadium, considered as a catalyst onto the magnesium grain. So effectively, the third class of material we consider LANET, light metal hydride. All the series of materials has been checked for, and so many experiments to determine the crystal structure and also to determine the kinetics and also the hydrogenation properties has been made. But as Non has said yesterday, for example, the most interesting one in the series is a sodium type of LANET. And so the sodium type of LANET is very interesting because of the stability against cycle, and also the low temperature of use, and also the hydrogen content. And the most interesting progress have been made by using a special type of titanium catalyst, for example, and consideration to the many catalysts already known and used in many groups in the world. So the nano size activated titanium appears as the best, probably the best of the catalyst, metal catalysts we can use to activate the sodium LANET. And so, for example, the cyclability, it is possible to deliver after, for example, in this case, a 10 cycle absorption-desorption, about 4.5 weight% of hydrogen. For example, a comparison to what it is known from literature by using ordinary, what I would like to say, ordinary powder of titanium. So the second type of activity consists to deliver the best of this type of materials to industry and to look how it's possible to upscale the production, it's possible to upscale the delivery of the best materials in mass. Not only a few grams as we process ordinarily in the lab, but in this case it was to produce 20 kilograms of materials. And this is a result we obtained recently with the best of the BCC type of material, and this result has been delivered by a Trebarer company that works in the consortium with us. And so it is to compare with, it is known as the best AB2 materials. So now we have, in this series of material, we have a good candidate to compete with the best AB2 type of alloy. Upscaling the second class of metal hydride, magnesium hydride, we work with the MCP company, French company. And so the work is done in two steps. First, it is necessary to prepare magnesium hydride with time, but to prepare this powder. And after that, so we dispose of a rotating furnace, and it is now quite automatized to produce this powder in mass. And after that, we use a very nice machine. It is a very energetic ball miller, and to upscale the production, so it is possible, for example, to ball mill several kilograms. For example, we work now with 1 kilogram per batch, but it's possible to prepare well-activated several kilograms of materials. So we have compared what has been obtained in the company, for example, the magnesium hydride, and so we have quite a nice comparable result in between the kinetics of absorption in the material we prepare by using a Fritsch ball miller in the laboratory and what it is prepared in a factory at scale of 1 kilogram, for example. So it's clear that now we can, at this scale, deliver a lot of materials. And so the question was, after that, what to do with this type of and this mass of material. So the next task in the work was also to deliver working materials. So in tank, so we have to build. To build tank, but before to build tank, it is necessary to consider many parameters we have to account for, because the mass transfer, the heat transfer, the kinetics, and the pressure, and so on. So many parameters has been considered, and so the group of Athens in our consortium developed a nice 2D simulation program, and it was used to simulate, for example, the low temperature behavior with time. This is on-time simulation, for example, and we can now plot a chart of different type of parameter, heat, front heat transfer in the mass of the materials, around, for example, cooling system. We have installed a cooling system in the tank. The mass transfer and the pressure and so on and so on. And all these parameters has been entered in the program and are now accounted for. And for the high temperature metal hydride for magnesium, so we have also developed the same type of simulation program. And also you can see, for example, here it is the cooling system in a tank, for example. And we have also a possibility to simulate on time, minute or second per second, what happens with the distribution of temperature in the tank around, for example, the cooling system. When hydrogen is introduced under pressure in the tank, the contour of reaction rate and also the contour of hydrogenation fraction and so on. So in time now we have a nice information about how to build or how to optimize a tank at the scale of a laboratory. And at the scale of the laboratory, we have built effectively a tank. It is installed in this system of furnace, for example, to activate the material first. And we have a lot of ancillary equipment. For example, we have a vacuum close to get a very nice vacuum on the powder and to get a very nice result and reproducible result, for example. And we have a lot of sensor, temperature, thermometer, and pressure sensor, and so on. And all this system is now connected to controlled by a computer. And so we are now looking to make a parallel between the numerical simulation and the effective experiment using this small tank. And this small tank, it is about a 1/4 liter tank, and developed only for simulation and to control the all parameters need to be controlled for the rapid charge and controlled discharge of hydrogen. And so you have detail on the mechanics of this tank. So this is, for example, a copper ring. It is a cryo cooler. This is a cooler in the tank installed, for example. It's possible to cool if you need at a given rate to cool down the overheat when you charge the hydrogen with hydrogen the hydride. So we have not only work on a small tank, but with a company Trebarer, a large amount of metal hydride was produced and also installed in this type of tank. It is a high capacity tank and 15 normal cubic meter there. And this tank is fully adapted for directly use to be used by fuel cell. And our application is installed in a glass Suzette in Stockholm. And for example, we have a solar cell, photovoltaic solar cell that deliver you electricity. And so we have an electrolyzer there, and electrolyzer can provide 14 bar hydrogen pressure. Hydrogen pressure is delivered to the tank, so the metal hydride tank absorbs hydrogen, and so on, and so on. And it is connected to all the use you can imagine in a building, for example, lighting, heating, and so on, and so on. And this is a very complex system, and so if you have no effective sun during some day, you can use, for example, biogas to activate fuel cell, and also you can also imagine that it is connected to the electricity net and so on. And this complex system works now in Stockholm. It's possible to get information on the website. And there is a very, very complicated but nice system to control all the energy sources and so on. So, because history is not definitively achieved, we have to continue the ongoing program and for several months. And so we have to optimize different parameters, for example, materials. We have to optimize materials in the 3 classes of material we consider. We have to optimize the tanks and also development of a very large tank, for example, by using techniques. By using magnesium, for example, and also to install a tank with a new BCC type of materials. So I would like to thank you for your attention. And I would like to thank also Sun to provide us a lot of energy.
Thank you very much. I think we take time for 2 quick questions. Are there any questions? Yes.
Okay. How this is just my personal curiosity. What about the quasi-crystal for the hydrogen storage material? I just ask you your comment. Quasi-crystal looks like your metal alloy. So if we use the hydrogen storage material,
as far as I understand, quasi-crystal can absorb hydrogen, just one composition, as far as I understand. In Japan, Professor Chai of Tokyo University, very famous in hydrogen quasi-crystal relations, and he found just one composition that can maybe absorb reversibly hydrogen. But the other thing maybe make disproportionate to hydride and the other intermetallics.
Yes.
May you say something about the safety problems with magnesium hydride, which is highly paraphoric?
Yeah, effectively, this is one I have not discussed of that because of limitation time, but it's very important to consider and upscaling the production of all the metal hydride, not only magnesium but allanite and also type of metal hydride. We have to consider to be cautious because of the very high reactivity, and if you have to manage kilograms of this type of powder, it should be done in a very nice system to transfer the powder in glove box and so on. So we have not so bad experience, but it's very difficult, for example, to manage the fire of metal hydride at a scale of kilograms. And so it's not exactly fire, but it could be explosive. And so in a industrial scale, I think metal hydride are not so simple to manage.
Okay, thank you very much, Daniel.
Now I introduce
Dr. Etsuo Akiba from AIST, Agency of Advanced Industrial Science and Technology Organization in Tsukuba. And he will present a paper on hydrogen storage using hydrogen adsorbing alloy. So, Dr. Akiba.
Thank you very much for your kind introduction, and good afternoon, ladies and gentlemen. I will talk about hydrogen absorbing alloys and their applications. So I will briefly introduce state of art of hydrogen absorbing alloys in Japan. Then I will show you some of examples of stationary applications of hydrogen storage alloys installed in Japan. And many of you are not so familiar with conventional or classical metal hydride. I'd like to introduce two topics on recent advance of those conventional alloys. And finally, I conclude my talk. The real industry of hydrogen storage alloys and nickel hydrogen batteries exists in Japan. And the sales in 2004, nickel hydrogen battery was 62 billion yen, or 466 million euro, or 310 million cells. But this number doesn't include numbers for hybrid vehicles. Last year, total sales in the world of hybrid vehicles was about 200,000 cars. For those cars, we need 45 million cells of nickel hydrogen batteries. And the size of the nickel hydrogen batteries for hybrid vehicles is about 5 times as much as conventional AA size batteries. It means 1/3 of total production hydrogen absorbing alloys were used for hybrid vehicles in last year. And we expect this year it must be 50-50. And I'd like to show you recent progress in nickel hydrogen batteries. One is materials. Sanyo company developed a novel super lattice alloys for nickel hydrogen batteries, and that type of alloy realized a capacity of 2,500 million mAh for one ASO. And this number cannot be reached by conventional AB5 type alloys. And also, Toyota Motor Corporation developed the third generation nickel hydrogen batteries for hybrid vehicles. So those are new topics for recent progress in hydrogen batteries. And Dr. Kuriyama mentioned the national project yesterday, but I briefly show you two projects related to hydrogen storage. One is the development for safe utilization and the infrastructure of hydrogen for 5-year plan conducted by NIDO. And under this project, various materials such as alloys, inorganic materials, organic compounds, and carbon materials are studied. But the target is on-board applications, and the 5.5% below 427 or 150 degrees C is the target. And this project is fuel cell vehicle-oriented ones. And universities and national institutes and industries contribute this project. The second project is the JHFC, Japan Hydrogen Fuel Cell Demonstration Project. It's a 4-year plan, and this is the last year, and conducted by directly NIDO, not METI. I belong to this ministry. And last year, 12 refueling stations were operated, and 15 fuel cell vehicles came to those refueling stations. And 8 car makers and 15 companies for infrastructures contribute this project. I just show you a density of the energy in conventional alloys and alanate and amide. Those values are measured by PCT method. Those are just theoretical values that I pick up from the literature. And this is the density of the materials. And this these are density of energy or density of hydrogen in a volume basis. And those values are included in a volume expansion measured by X-ray diffraction, neutron diffraction method. And you can compare the density of energy in those hydrides. Still conventional metal hydrides are superior than those advanced, newly advanced aranids and amide. And I'd like to show you three examples of hydrogen-differing application of the metal hydride or hydrogen-absorbing alloy for hydrogen-differing station. This is the first one that built in 2002 in Osaka City under the old WINET project. It was finished 3 years ago. 3 companies collaborated to build this nice refueling station. Hydrogen was produced by reforming from natural gas and purified this unit and stored this metal hydride storage tank. Of course, there is a chiller to provide cooling water for onboard metal hydride tank. And this is a high-pressure storage and compressor in this building. This is a detailed photograph of storage unit installed at the Osaka station. Capacity is 90 cubic meters, and the absorbing rate is 1 cubic meters per minute. It depends on the performance of the reformer. And the desorbing rate is 5 kiloliters or 5 cubic meters. It equivalent to 0.4 kilogram hydrogen per minute. And the pressure is 0.6 megapascal, and the size is something like that. They use mission metal type AB5 alloy, and the total weight was 650 kilograms. This is the second one, and this hydrogen differing station was built in Takamatsu City at the same year to the first one. And this is a different type of differing station. Hydrogen is generated by electrolysis of the water, and hydrogen was stored in this unit using metal hydride. In this case, capacity was 75 cubic meters, and the hydrogen pressure was 1 megapascal, and the desorbing rate was 3 cubic meters per minute. In other words, 0.25 kilogram per minute. I'd like to show the third example of a refilling station. This is built under the JHFC program at the Ariake refilling station. They store hydrogen in the form of liquid, hydrogen. The size of the liquid hydrogen tank is 10,000 liters in liquid, and the boil-off rate is about less than 1% a day. They use a metal hydride tank to recover volume of gas from this liquid hydrogen tank. Its size is just 25 liter in liquid phase or 20 cubic meters in gas phase. They recover BOG gas, boil-off gas, and compress to 40 megapascal and supply to a compressed gas cylinder. And this is a detailed photograph of recovery of boil-off hydrogen using metal hydride. There are 2 storage tanks. The capacity is 10 cubic meters each, and the outlet pressure is 0.10 megapascal. They use AB5 type alloys. In total, 140 kilogram of AB5 type alloy was used. And I'd like to move a little bit more scientific part, and I'd like to introduce 2 examples carried out by my group on hydrogen absorbing alloys. One is the superlattice alloy. Toshiba company developed new type of alloys for the negative electrode of nickel hydrogen batteries. And last year, Sanyo started to sell nickel hydrogen batteries using this type of superlattice alloy. That seems to have the same or very similar crystal structure to the alloy originally Toshiba developed. The capacity of the battery reaches 2,500 mAh for one AA cell that cannot be realized by the conventional alloys. So this is the discharge capacity of one superlattice alloy. This is a superlattice alloy, and this is a conventional AB5 type alloy. About 20% of capacity is larger than conventional alloys. And we prepared two different chemical composition of superlattice alloys using frequency induction melting method and argon gas. And this is an XRD pattern of one of the samples. If we look at very low theta region, we found two phases with very large lattice parameter. A phase has 24.4 angstrom, and this phase has 24.5 angstrom. So it's very difficult to use powder diffraction method or Rydberg analysis to distinguish two phases and determine its crystal structure. So we moved to single crystal analysis because alloys consist of two phases with large lattice parameters. Powder diffraction cannot be applied. So small single crystal-like pieces were picked up from crushed alloys. The precision photographs were taken to confirm the crystallinity of the pieces. So it takes a long, long time. It's very time-consuming, and it's very hard work for the scientists to pick up very nice alloy from the crushed alloys. But anyway, we succeeded in determining this kind of structure. This structure consists of two units. One is AB5 unit. Another one is A2B4 unit. It's a Laves type unit, and this is a Rothamnick type unit. This is stacking in this C direction. And we found magnesium only occupied the site of A2B4 unit. In other words, Laves type unit was occupied, magnesium occupied only A2B4 unit. The reason is very simple. Lanthanum magnesium distance in this unit is 3.19 angstrom. If we compare atomic radius of magnesium and lanthanum, only magnesium can occupy this site. But in other AB5 type unit, only lanthanum occupies those sites. We can easily distinguish this bond direction, 3.85 angstrom, between two AB5 units is just a double of this value. And this structure can be described by space group of this one, and lattice parameter is just a 5.04 angstrom in A axis, but C axis is 32 angstrom. It's very, very long. And we found three different types of stackings in two alloys. So in one alloy, we found this type and this type, Ce2 nickel 7 type and Pu nickel 3 type of alloy, type of the crystal structure in this alloy, and this type of C nickel 7 and PL5 CO19 phase was found in this phase. And the magnesium occupies that Laves phase type unit, and this occupation stabilizes the structure for repeated hydrogenation. And new groups of alloys with various stacking of Laves and AB5 type unit were found in this study. And Daniel gave us some nice introduction of our Laves phase related BCC alloys. I just mentioned we use only second plateau between monohydride and dihydride. Dihydride has a calcium F2 type fluoride structure, but the crystal structure of monohydride is a serious problem. And we found titanium vanadium manganese alloy. It starts from a BCC structure, but in monohydride it has FCC structure in metallic sublattice. And in this case, sometimes shoot FCC, and in some cases real FCC. It depends on the chemical composition. But dihydride has a FCC structure. And monohydride has a sodium chloride type structure. It means metallic sublattice was formed by FCC phase, and in octahedral site was occupied by hydrogen. This is a sodium chloride type structure, and this is the first time to find out this kind of structure in the hydride of the transition metal. But if you put much more hydrogen into this lattice, hydrogen moving from octahedral site to tetrahedral site and form CF2 type structure. And this is a kind of summary of titanium vanadium type BCC alloys. All the alloy has a BCC structure, and all the dihydride has a FCC structure or calcium fluoride type structure, but monohydride are different with chemical composition. That is the key issue. To design new type of BCC alloy suitable for our applications. So I'd like to conclude my talk. For stationary application, energy density is a key performance of the materials. So hydrogen absorbing alloy is one of the most ideal candidates. And heat management is indispensable, but a solution has been proposed in this conference. Dr. Mori of Toyota Motor Corporation showed a very nice and engineering solution of metal hydride, or heat management of how to cancel or how to treat heat of formation of the metal hydride. And under the Japanese national project, stationary applications of the alloys have been developed, especially hydrogen storage in hydrogen refilling stations. And research and development of hydrogen absorbing alloys are active in Eastern Asian countries because nickel hydrogen batteries, which are used for hybrid vehicles, are commercially produced only in those areas. Thank you very much for your kind attention.
Any question about this presentation and the development in Japan? Yes, please.
Just a quick question. You had a capacity of 5.48%, and the temperature you specified should be below 427 degrees Kelvin. That's 154 centigrade. What's the basis for that temperature? Why 427 K, less than 427 K? Yeah, they need that. I mean, where does that number come from?
You mean the national project?
Yeah.
I'm not sure because I'm a scientist, because I'm not responsible to that value. But anyway, from the at the end of the WINET project and the starting of the new project, 5.5% at 100 degrees C seems to be very severe. So they gave us some room to be considered. So 50 degrees is such kind of room for the scientists. That's my personal opinion.
Thank you.
Keith?
Yes? Keith?
I was interested in your superlattice structure.
Yes.
Does the hydrogen go into the, presumably a lava phase layer with the magnesium, or into the AB5 layer?
Frankly speaking, we have not measured the neutron diffraction because it's very difficult for make a big crystal, single crystal. And the powder is not so easy at this moment. But we measured PCT. And from the PCT, hydrogen should enter both AB5 and A2B4 unit. Otherwise, such large numbers of hydrogen capacity cannot be reached.
It's rather similar to the yttrium cobalt-3 system that we've been looking at, and in that it goes into the AB5 first, and this actually generates a number of different phases in the absorption process, which would not be ideal.
But we found a very nice, just one very, very flat PCT or plateau region.
So it must go into both at the same time. Thank you.
No more question? Ah, yes.
is I want to know, your hydrogen storage system is used for the proton exchange membrane fuel cell cars running for experiment or for what other purposes? You mean our... Those you shown on the figures, yes. Yes, both. I showed 3 refueling stations. 2 was constructed under the WINET project, 1 is the JHFC project. All the stations were built for refueling hydrogen to fuel cell vehicle, polymer electrolyte fuel cell vehicle. So that's really using right now, is it? Yes. For running those cars? Yes, especially Ariake refueling stations, they refuel to the public bus operated by Tokyo Metropolitan City. Yeah. And what is your most successful kind of alloy you are using right now? There must be some improvement, just Daniel said. But they still use an AB5 type alloy because it's easy to handle. Also, our industry has a lot of experience how to change their properties, such as current pressure and working temperature, something like that.
No more questions. So we have to go to the last talk.
The next talk will be presented by Professor Alexei Mitrokhin from Moscow State University. So, can you please begin?
Thank you, Anatoly. First, I would like to thank the organizers for this good opportunity to address such interesting conference with our results. Well, so actually, Daniel and Itsuo just said some words instead of me on stationary applications of hydrides. So my task is much easier now. Sorry. Yeah. Oh. Let's start from the beginning. Well, so the metal hydrides for hydrogen storage are known for more than 30 years, and certainly we all know that hydrogen storage utilizing the metal hydride technology offers several benefits over conventional technology. Among main, we can name high volumetric energy density. Metal hydrides are rather compact, and still the concentration of hydrogen atoms in them often exceeds the density of liquid hydrogen. Second important benefit is the possibility of low pressure operation while refueling or hydriding these materials. We can use hydrogen produced by electrolyzers or just from the gaseous hydrogen tank, and in this case we don't need any high pressure compressor. Another important moment is that in some practical applications we can use the generated waste heat, for example from fuel cell or from any hydrogen engine, and this can reduce the whole system cooling. But why we turn mainly on stationary applications? That's quite clear because storage requirements for stationary applications are typically less stringent for those which are required for onboard storage. So what are main groups of applications for stationary storage? First, it's the large-scale hydrogen storage, and one of most famous examples, that's the German project of 80s of the last century, when they built the storage system for 2,000 cubic meters of hydrogen. Another big group of applications, that's heat pumps, compressors, and refrigerators. And well, a lot of work on this subject was done in Japan, and Dr. Akiba just showed us a lot of devices which existed just now. Hydrogen recovery and purification, as well as laboratory storage systems. In this case, I can address you to yesterday meeting, and the latest examples were presented by Professor Miloshenko and Dr. Barzenko. One important moment is that practically in all named realized applications, usually AB5 type alloys were used as storage media. However, titanium alloys, and especially titanium Lewis phase based alloys are very interesting for storage of hydrogen. The main reason for this is that two basic binary compounds for modeling of these alloys, and that is titanium manganese 2 and zirconium manganese 2, both show wide homogeneity ranges of Lewis phase. In case of titanium manganese, it's from 64 to 70 atomic percent of manganese. In case of zirconium compound, it's from 26 to 34 atomic percent of zirconium. Well, in our work, we showed that the same wide homogeneity range also present in ternary system, zirconium, titanium, manganese, and even in more complex systems such as titanium, zirconium, vanadium, manganese. The main benefit of this homogeneity range and the use of non-stoichiometric Lewis phase alloys is that we can simply use the existing components of alloy for substitution of, for example, titanium and zirconium by manganese, or vice versa, titanium instead of vanadium and manganese. Thus, we have possibility not to add any other metals to change or improve the hydrogen absorbing properties. Well, in our investigations, we employed a lot of alloys, and this allowed us to find some interesting dependencies. For example, in this case, we can see that the desorption enthalpy of the reaction, if plotted versus cell volume of initial alloy, we can see the tendency that the absolute value of enthalpy increases with increasing cell volume of alloy. In case of desorption, the same dependence for desorption pressure versus cell volume. This independence is much more clear, and even one can say that it's almost linear. If we analyze this data, we can see that there is some important value can be found, and this value is the cell volume of about 160 cubic angstrom. At this moment, the desorption pressure, for example, at room temperature, reaches the value of about 20-30 atmospheres, and this can be considered as the upper limit for any practical application, and usually is used even in laboratory experiments to investigate the absorbing and desorbing properties of alloys. In fact, all these rather simple dependencies, they clearly indicated to us that there should be some simple way to model new alloys in these wide homogeneity regions. The base for this model is quite simple. If we consider the binary metal system, then we can see that, for example, lattice parameters of alloys within the range of solid solution will change almost linearly with slight deviations according to Wegener rule. If analyzing our data and the data available in literature, we also noticed that even such complex parameters as enthalpy and entropy of reaction with hydrogen, they also change monotonously. But when we turn from a binary system to multi-component alloys involving 4, 5, or even more metals, you can't make the prediction just on the sheet of paper, and the only reason is that the change of concentration of any metal will obviously give change to the concentration of all other constituents. But since all these changes take place monotonously, we decided that it is possible to use, just for first approximation, just the second power equation. And this equation, you can see that Fc, that is the parameter such as lattice parameter or enthalpy or entropy. All C's, that's the concentrations of the constituent metals, and A's are just the coefficients of this equation. If we have enough literature data, so-called database with specific values of this parameter connected with the concentrations of metals, then we can solve the opposite problem, and just to find first the coefficients of this equation. And that's the first step. The second step is that we can calculate the needed parameter for any other alloy in the range of solid solution. Actually, we can see that our model and our equations give rather good results, and here we can see the comparison of calculated and experimental values for enthalpy, entropy of reaction, and even for equilibrium desorption pressure for some alloys of ternary and quaternary systems. And we see that we have very good correlation of calculated and experimental values. Well, in fact, after that, we just calculated the whole range of possible equilibrium pressures for these ranges of Lewis phase homogeneity in ternary and quaternary system, and you can see it here. Well, in fact, the main idea of this model was just the practical use, because in any case, when you turn to practical applications, you have a variety of problems, and in each problem there is the specific input parameters, meaning the available temperature range of heat and cool system, and the available pressure of hydrogen, which is used for filling the storage unit. Well, and well, concluding this talk, I must say that this work was done for several years in collaboration with our colleagues in France, Switzerland, Austria, and United States. Also, we had good collaboration with some Russian institutions, but well, this field of research is not closed for us just now, but still we have two more directions of collaboration. First one is the research of materials for hydrogen storage at super high gaseous pressure of hydrogen, up to 3,000 bar. And the second is the research of materials for hydrogen storage at high hydrostatic pressure. Thank you for attention.
So, any question, please, or comment? I do not see. So, no question. So maybe it's no question. Oh, sorry. Yes.
Just a quick one. What are the particular applications you are interested in to study the hydrogen storage at 3,000 bar, as you mentioned there in the last slide, and the other one, the other application? What do you have in mind? Why are you interested in studying those?
Well, if I understood quite clear, this is mainly fundamental research, but as we plan in this research, we can find some new types of hydrides, not necessarily new type of intermetallics, but surely new types of hydrides, well, as we call them now, supercapacious. And there are some hints that the use of high pressure can seriously change, all the situation. For example, a well-known fact that titanium chromium 2 or titanium chromium 1.8 being hydrided up to 100 atmospheres at low temperature, it will give just conventional hydride of Lewis phase. But if you apply pressures up to 1,000 atmospheres, you will get a new hydride, and I don't remember correctly the mass percent, but the formula is something like H5.3. You can easily calculate. and these give, well, some another meaning. But certainly one can say that it's practically not so interesting to use such high pressures in practice. But as you remember, for example, artificial diamonds were first synthesized at, I don't remember how many gigabars, but now we can produce them almost in vacuum. So.
Any more questions? So, oh yes, okay.
I'm a comment on this question, and I and Dr. Mori presented the concept of the hybrid tank, but the hours for the hybrid tank operated around up to 30 or 40 megapascal. But when we develop the metal hydride for the hybrid tank, we need to measure the property up to one node higher pressure to find appropriate material or metal hydride with potential to such application. It's a very good technology for such application for your activity.
Yes, certainly. That's very interesting because no one knows right now what will be at 700 bar. Yeah.
Okay. Any more questions? And so, no, just a case in order to thank again a speaker.
Okay, then I think we continue directly with the panel discussion. So could the rest of the members of the panel come up here now? Okay, so the topic is off-board storage, stationary application, and hydrogen transport. We have decided to, I mean, there are many links to the other sessions. I mean, both on chemical hydrides and on the. So we have decided to try to keep this discussion for the interstitial type of hydrides and for magnesium-based compounds. So there are then of course several questions that can be raised both with respect to the materials and applications, interests for industry and things like that. And of course the major goal, again to repeat that, I mean that is the goal for this panel discussion, is to try to find some possible IPHE products. So I think we start, Perin has prepared a short introduction to this. So,
yes, I wanted to just introduce and stimulate the discussion so about this the off-board storage and stationary application. What I call it's a collection of niches before we get to the car industry and